Hi friends, welcome back. Today we're talking about permutations versus combinations when it comes to probability. And this really confused me when I was your age, so I'm hopeful that as I walk you through these, it will make a little bit more sense to you than it did to me when I was learning geometry and algebra 2. So grab your notebook. I'm going to give you a lot of notes right off the bat so that we can start, and you're going to want to write this down. So the first one that we have is our permutation and combination. The difference of the two is permutation, your order matters. Those positions are unique. Combination, your order doesn't matter and the positions are all the same. So make sure to copy this information down, especially these formulas. The N represents the number of objects available. The R represents the number of positions available. So the other thing that we want to talk about are general probability notes. Remember, probability is just the favorable outcomes out of over the total possible outcomes. The other things we want to remember is the word and means multiply and the word or means add. If you're adding, you also have to check for any overlap and subtract those if necessary. Okay, so once you have those down, let's launch right into it. First problem that we have is how many ways can 15 runners come in first, second, and third place? How many ways can 15 runners? So the first thing you want to ask yourself is this a permutation or a combination? And again, the difference there is, does the order matter? And in this case, it does, because each position, first, second, and third, those are all different positions. So this one would be let me show you, permutation, because order matters. So we would say there are 15, and then we say P. Now, how many positions remember the R is the number of knocking things over. The R is the number of positions open. And so the number of spots that we're looking to fill is first, second, and third. That's 3 spots. So 15P3. Okay, so the way that we would write that down is we do 15, and then we find, for the bottom, we find the difference between these. So that's going to be 12. Now, if I wanted to do this all the way out by hand, I would have upstairs 1 times 2 times 3 times 4, all the way till 12, right? And then I have 13, 14, and 15. Downstairs, I have 1 times 2 times 3, all the way up until 12. So you can see that this cancels out with this, and I'm left with 13 times 14 times 15. And if I plug that into a calculator, I end up with 2,730. Some calculators will allow you just to plug it in like this. You don't even need to do the formula. Some calculators will do the exclamation point. You can type it into Google with the exclamation point and it should work. You may even be able to type it in like this, but either way, just make sure you know how to do it by longhand here, like I've just done on this one. Okay, let's take a peek. Okay, so there are 2,730 different ways that 15 runners can come in first, second, and third. All right, there are 12 seniors on student council. How many ways can they be selected? President, vice president, secretary, and treasurer. Now, these positions are unique, which means the order matters. This is another permutation. We have 12 seniors and we have 4 open spots: president, vice president, secretary, and treasurer. Okay, so that's going to give us 12, and then we find the difference between the two. So I'll write it down this time so you can see. So we end up with 12 over 8, just like that. And if we plug that information in, we end up with 11,880 different ways that we can select those 12 seniors into positions, the 4 unique positions. Okay, let's talk about, so those are examples on that permutation. Now let's talk about combinations. So for combinations, we have this. How many different ways can 2 students be selected from a class of 24 to clean up at the end of the period? The nice students who will help clean up at the end of the period. Okay, so how many ways can we select 2 out of the 24? The order doesn't matter. I don't care if you pick Susie and then Joe, or Joe and then Susie. The order doesn't matter there, and those positions are not unique. They are the same position. So that's how we determine it's going to be a combination. So we have 24 combo 2. And the way this one looks is we do 24 over 2, and then we find the difference between those. So 22, because the difference being 24 minus 2 will give us 22. And again, you can plug this into a calculator. 22 and 24, that means upstairs we're going to have 23 times 24, and then this would be canceled out with the rest of those 22s, over 2 times 1, because that's this thing right here. So if you plug all of that in, you end up with 276. So there are 276 ways to choose 2 students out of a group of 24. Another combination one. There are 7 students working in a group. How many ways can the teacher choose 3 of them to present? So we have, again, we don't care what the order is. All the positions to present are unique, or not unique, are all the same. So combination, and we say 3. So we end up with 7 over 3, and then we find the difference between those two, 7 minus 3, which is 4. So we end up with 7 over 3 times 4. Plug that into your calculator, and we end up with 35 different ways that the teacher can choose those groups. Okay, so hopefully that kind of helped with that one. Now we've got some other ones that get a little bit harder. So let's talk about these guys. Familiarize yourself with a deck of cards. And in this case, we're going to find the number of possible 5 card hands that contain the cards specified. So let's say we want 5 face cards. Now you've got to think about, you have all 52 cards in front of you, right? The number of face cards that there are is 3 face cards for 4 suits, right? There's the Jack, King, and Queen. So that's 12. So in the 52 cards that you have in front of you, there's only 12 that fulfill this, which is face cards. I want to know how many different ways we can take those 12 cards and have them in groups of 5. Now, I don't care about the position here because I want to know of those 12 face cards, how many different ways can I have select 5. So it doesn't matter which gets picked first, second, or third. They're all going to be in your hand and they're going to be mixed around. So that is a combination. We have 12 total face cards and I want 5 of them. How many different ways can I have 5 of them? That's going to give us 12 over 5. And then you find the difference between the two. So that's 7. And if we plug that into our calculator, we get 792 different ways. So there are 792 ways to take those 12 cards and find combinations of 5. All right, what about 1 ace and 4 cards that are not aces? This is really key here. Look at this word, and. Remember, and means multiply. I could never remember how to think of, how am I going to remember that? You would think and means addition because they both start with A. No. It's and means multiply. So if you're thinking and addition, no. So we're going to multiply these. So the first thing we need to do is, we have our deck of 52 cards in front of us. How many of them are aces? There are 4. I want 1 ace. So that's going to be 4 possible, and I want 1 of them. And means multiply. And then 4 cards that are not aces. So of the 52 cards that are in front of me, 48 of them are not aces. 48. And I need 4 more of those. Okay? So if we do that, we end up with 4 over 1, and then find the difference, times 48, over 4, and then find the difference, 44. Plug all that into our calculator, we essentially end up with 4 times 194,580, and that gives us 778,320 different ways to have 1 ace and 4 cards that are not aces. All right, what about this guy? 5 hearts or 4 diamonds. Remember what I said, the word or means add. So when you see this word generally in these guys. So so our or here means that we need to do 5 hearts first. So again, we have all 52 cards in front of us. How many of those satisfy the hearts? Well, that is going to be 13 because there's 4 suits and one of them is hearts. So 13 cards, and I need 5 of them. Or I need diamonds, and that's going to be 13 out. I need either 5 hearts or 5 diamonds, any combination of those. That's why we're adding them together. So we end up with 13 over 5, 8, plus 13, 5, 8. And if we plug those into our calculator, we end up with 1,287 plus 1,287, which gives us 2,574. 2,574. Okay, one more. All right, let's see this one. Each player in a game selects 4 letters from the alphabet. 4 letters are then drawn. The letters cannot be or the letters cannot repeat, and the order does matter here, okay? So we know we're going to be dealing with probability because the order matters. You win the big prize if your 4-letter code matches exactly the one drawn. What is the probability you've chosen the correct code? All right, well, first let's think about, this is probability. So we're going to say there's 26 letters in the alphabet, 26 letters, and it's got to be a permutation. I think I said probability. I meant permutation. And we're picking 4 of those out of that 26. So how many different ways can we have 4 letters arranged from 26 without repeating? All right, so if we do that, we end up with 26 over 4. Whoops. Sorry, permutation, not combination. 26 over 26 minus 4, so that's going to be 22. And if we do that, we end up with 358,800. Now, be very careful here because the question asks, what is the probability you've chosen the correct code? Now, remember, basic probability is favorable over total possible. So your answer is not 358,800. It is 1 out of 358,800 because there are this 358,000 possible, but only one of those is the correct answer, the correct 4-letter code. All right, you win a small prize if your 4-letter code starts with the same letter of the chosen code. What's the probability both your code and the winning code starts with M? Okay, so the total possible. So again, we want favorable over total possible. So the total possible is fairly easy because, again, permutation matters here. We have total possible is 26 permutation and 4 because we have 26 letters and we need to select 4 of them. So again, this is going to give us the same thing down here, which is what we just had, 358,800 because we literally just did that, right? 26, 4. Now, this one's a little bit different. We want to know, of those 358,800, how many of those start with the letter M? Well, the way that we are going to do this is we're going to take M out of our alphabet. So we are now down to 25. And then because M is in that first position, I don't care about 4. It's going to be 3 because all I'm worried about are the 3 that come after that first M. And I can only pull from this pool of 25 because we've already used the M, the 26th letter there. So if I were to do this, my permutation here, plug that into our calculator, we get 13,800. So the favorable over our total, if we divide that out, we end up with 3.85%. So you have about 3.9% chance of both starting with M. Hopefully that makes sense. If you have any questions, leave them down below. Otherwise, we will see you next time.